To understand the economics of the space industry, look at the physical output of a launch vehicle's exhaust plumes. Lifting mass off the surface of this planet requires SpaceX, for instance, to burn roughly 2.65 million liters of fuel every single second during ascent. Delta V is the velocity change required for orbital maneuvers. Reaching low Earth orbit demands a staggering 8.0 kilometers per second. Compare that to heavy surface industry. Moving thousands of tons horizontally via cargo ship requires a delta V approaching zero. This kinetic energy penalty dictates the limits of aerospace engineering. Because every single component must be launched at an enormous fuel cost, orbital infrastructure remains severely restricted in volume and mass. As long as humanity relies on pulling raw materials up out of Earth's gravity well, large-scale space development remains mathematically constrained by the weight of its own fuel. Near-Earth asteroids represent massive deposits of fundamental building blocks, iron, silicates, and water, drifting freely through the inner solar system. Because they are small, their gravity wells are negligible. Moving material from an asteroid to Earth orbit requires a fraction of the kinetic energy needed to lift that same mass off Earth's surface. But extracting those resources presents a distinct mechanical problem. Down here, heavy excavation relies entirely on Earth's gravity to generate the traction, leverage, and friction necessary to break rock. The modern commercial aerospace sector does not intend to bring asteroid metals back to the surface. The goal is in situ resource utilization, harvesting the materials to build infrastructure directly in orbit. This has led to the assumption that mining an asteroid simply involves landing a drill on a rock and turning it on. In a microgravity vacuum, every mechanical assumption about excavation fails. Moving heavy industry into space requires redesigning extraction from first principles. The first physical barrier is the kinematic constraint. Without weight, machinery has no natural leverage against the ground, and friction effectively drops to zero. This diagram shows drilling without gravity. If a rover applies downward force to a drill, the rock generates an equal upward force, lifting the machine. The drill's rotational torque then transfers directly into the chassis, sending the spacecraft spinning into the void. Before ore can be excavated, the spacecraft must establish a rigid structural anchor to counteract the forces of its own machinery. One architectural approach uses a harpoon tether system. The spacecraft fires tension cables into the rock, pulling the platform tightly against the surface. Asteroid Mining Corporation takes a different approach with their SCAR-E robots. These machines deploy mechanical claws engineered to grip the uneven rock and lock the chassis in place. Solving the kinematic constraint proves that in a vacuum, forcing a vehicle to remain stationary requires just as much active engineering as propelling it forward. Even with a secure anchor, physical drilling generates a secondary environmental hazard, asteroid regolith. Because asteroids lack the weathering effects of wind or flowing water, the dust on their surface is highly abrasive, glassy, and prone to static clinging. In a microgravity vacuum, pulverized rock behaves aggressively. The kinetic disturbance of a drill throws up an expanding permanent cloud of sharp crystalline shards. This persistent abrasive cloud threatens to coat solar arrays, block thermal radiators, and grind down mechanical seals. Multi-minute communication delays between Earth and the asteroid mean these machines must operate autonomously. If a robot cannot manually clear a dust jam, kinetic drilling becomes too risky for extraction. To eliminate these hazards, engineers are abandoning physical force and relying on thermodynamic phase changes. The company TransAstra targets Type C carbonaceous asteroids. These specific rocks contain high concentrations of frozen water and hydrated minerals. This diagram outlines their optical mining architecture. The spacecraft approaches the target and deploys a flexible, airtight envelope, completely enclosing the asteroid to establish a controlled environment. This specific capture bag technology is already space-tested. In 2025, engineers validated the material integrity of these enclosures aboard the International Space Station. The spacecraft then deploys massive parabolic mirrors, focusing intense sunlight directly onto the rock. This extreme heat vaporizes the trapped frozen volatiles. The gas drifts away, strikes the cold inner wall of the bag, and immediately condenses into liquid water for storage. By utilizing concentrated light and vacuum thermodynamics, engineers can harvest tons of raw propellant without a single moving part ever touching the asteroid. Water is essential for propulsion, but structural infrastructure requires heavy metals. Extraction models shift to Type M asteroids, which are dense with iron, nickel, and platinum. Harvesting these metals reveals the massive economic hurdle of mass return missions. Bringing raw, unrefined ore back to an Earth-orbiting facility is highly inefficient. This transit map shows the orbital costs. Navigating from low Earth orbit to a near-Earth asteroid and back requires 5.5 kilometers per second of delta V. Returning thousands of tons of useless silicate rock alongside targeted metals breaks the mission's mass budget. Astroforge solves this mathematical problem by completing the refinement process on site before the return trip begins. Without a gravity well, microgravity separation techniques change everything. Purified liquid metals naturally cool into dense spheres, allowing lighter rocky slag to be vented away. This ensures that the spacecraft only expends its return trip delta V on hyperdense, highly purified payload. Space mining is an extraction challenge, but success dictates a rigorous exercise in optimizing orbital mass ratios. Humanity has retrieved asteroid material before, but legacy scientific missions operate on a model that is incompatible with industrial scaling. Historically, aerospace agencies deploy bespoke, custom-engineered probes. A mission like OSIRIS-REx requires over $1 billion and years of highly specialized development to return roughly 120 grams of sample material. Startups like Karman Plus are abandoning custom avionics. They modify off-the-shelf equipment and use autonomous optical navigation to dramatically reduce the development cycle. Instead of spending a decade analyzing one specific asteroid, they use a probabilistic model, targeting mathematically likely candidates from a database of over 1 million known near-Earth objects. This operational shift drops the cost per kilogram of asteroid material by magnitudes. It transitions space extraction from a scientific experiment into a repeatable commercial utility. The primary objective of this architecture is to supply orbit with bulk mass, rather than supply Earth with rare metals. This orbital map visualizes the target end state. Supply lines connect near-Earth asteroids directly to orbital nodes, supplying trans-astra tugs running on asteroid water and habitats constructed from Astroforge steel. Producing structural components and radiation shielding directly in space entirely bypasses the energetic bottleneck of launching mass from the ground. The utility of an asteroid is measured by the volume of infrastructure it enables in the void, far removed from its market price on the Earth's surface. Mastering the physics of microgravity extraction is the final engineering hurdle required to permanently sever humanity's dependence on the Earth's surface.